We are a group of second year aeronautical engineering students at Imperial College London. Our group design project for this year was to design, build and test a wind turbine.
This video will take you through the process of how we design our turbine using computer-aided design, manufactured our components, and finally tested it in a wind tunnel.
The design constraints of the project are to construct a horizontal axis two-bladed wind turbine with a maximum diameter of 800 mm and an anti-clockwise rotation from the wind direction. Upon receiving the project brief, a lot of research was required as we did not know much knowledge about wind turbines and their designs. Once an initial idea was achieved, we started dedicating jobs and setting time frames to finish our preliminary design. The first step we needed to take was to select an aerofoil. From the aerofoil database available online, we wanted to choose one that has the best lift-to-drag ratio. This was done with the help of the program Exploit. By analyzing the data obtained for each aerofoil series, we concluded that the SG series was deemed to be the best choice for small-scale wind turbines. Out of the series, the SG6043 aerofoil was chosen as it has the largest stall angle compared to the rest. However, we thought that the SG6043 might not be able to withstand the stresses at the root, as it was not thick enough. Therefore, we decided to use the thicker SG6040 aerofoil for the sections nearer to the root.
For the aerodynamic design of our blade, we created an Excel spreadsheet which generated the values for our aerodynamic forces and output power for different input values of airspeed, rotational speed and blade profiles. The pitch angles and chord lengths for different segments of the blade were then calculated, with the largest pitch angle of 40 degrees at the blade root, and this was being reduced to almost zero twist at the tip. The maximum chord length was selected to be about 10 mm, roughly at a distance of about 70 mm from the hub. This is because at the hub the blade speed is much lower than at the tip, so the power captured will be much less. So therefore, by having a larger planform area close to the hub, power output can be maximized. The pitch angle and chord length were then reduced gradually to prevent a large increase in aerodynamic load, while increasing blade speed to generate power. For the tip speed ratio, it was to be in the range of about 4 to 6 according to theory, and our calculations were giving us values between 4.5 to 5.2. So after we had our chord and pitch distributions across the entire blade span, we used a wind turbine design software called Q-Blade to simulate our blade design, including the two aerofoils that we had selected earlier, SG6040 and SG6043. So these two aerofoils were inputted into Q-Blade along with the other calculated values, and they were optimized using the basic blade element momentum test. The test, which was run on Q-Blade, helped us to analyze the forces and power output of the blade, following which we decided our optimal TSR to be 4.8. We modeled the blade design using the CAD program Creo Parametric 2 and using the blade geometry we had calculated earlier. So using this CAD model, we measured various parameters that we would need for our structural analysis, such as cross-sectional areas and moments of inertia at the various radii.
We calculated relative wind velocities and values of lift and drag coefficients for each of the blade elements, which were then used to obtain their respective axial and tangential forces. Next, the engineer's theory of bending was used to approximate the blade as a beam in order to calculate the bending moments for the axial and tangential directions. Following this, the equations for circular motion were used to find the centrifugal forces and subsequently the stresses for each of the blade elements. From our calculations, we saw that the stress values on the blade were lower than the peak tensile failure stress of ABS plastic, therefore it was structurally sound. As we approximated the blade as a beam, the structural calculations might not have been accurate. Therefore, as a safety measure, we decided to increase the chord length of the blade at the section which blended with the root to further reduce the stress. We also increased the pitch angle for this section to increase the lift and power output. We used milling and lathe machines to manufacture the aluminium hub. Next, we used rapid prototyping to manufacture the blades. Our CAD drawings were imported into a 3D printer which produced the parts made from ABS plastic. Due to the limitations of the printer, we had to section the blade accordingly using dovetails. After the sections were made, we glued them together and then sanded the entire blade to reduce the rough surfaces created by the printer.
Once the manufacture was complete, the turbine was tested at various wind speeds in the Honda wind tunnel. Before the test began, the wind turbine was allowed to spin freely until it had registered its maximum RPM. An electromagnetic brake, called a hysteresis brake, applied a controlled mechanical resistance to slow the turbine to its minimum operating RPM. The wind tunnel controller was then preset with these values of maximum and minimum RPM. We started the test by adjusting the wind tunnel to one of the required test speeds. Again, we allowed the turbine to spin freely until it had reached its maximum RPM. The hysteresis brake applied a controlled deceleration to the turbine, whilst torque and RPM were measured. When the preset minimum RPM was reached, the wind turbine was accelerated via a controlled reduction in braking resistance. Throughout the test, continued measurements of RPM and torque were taken, and we repeated this procedure for wind speeds of 6, 8, 10 and 12 meters per second. Our wind turbine successfully completed all stages of the test without structural failure. During the 12 meters per second test, we observed that the free spinning RPM was quite high. At the highest RPM, the angle at which the relative wind struck the blades was increased, and this caused stalling to occur, which decelerated the turbine. As the turbine slowed down, the relative wind angle went back down and the turbine increased its speed again until stall. We think the stalling behaviour observed may act as a passive stall control system, preventing potential structural damage to the turbine at higher wind speeds. However, we also observed that this stalling behaviour occurred in a periodic manner, causing vibrations in the structure of the turbine. From the test we carried out, we don't really know if the vibrations would increase at high wind speeds, and we know that excessive vibrations could eventually lead to structural failure. Therefore, we would suggest testing our wind turbine at wind speeds beyond 12 meters per second to investigate this further.
Our recorded data was processed to produce a graph of power coefficient versus TSR for each of the wind tunnel test speeds. As you can see from the graph, our turbine achieved a maximum power coefficient of 0.242 at a wind speed of 10 meters per second. The TSR of our wind turbine at this point was measured to be 7.2, which is considerably higher than our target TSR of 4.8. This has led us to believe that the initial design TSR, which we quoted early in the design process, was inaccurate and does not correspond to the wind turbine we actually designed. We think that the design of our blades caused the TSR to be too high, causing tip-end losses and losses due to the blades flowing through turbulent air. Further problems with our design associated with a high TSR were especially noted during the test at 12 meters per second. These include noise generation, vibration, stalling of the blades, and exceeding the maximum design RPM of 3000. This leads us to conclude that our wind turbine may not be suitable for use at higher wind speeds. To improve our design, we would suggest altering the design of our blades to reduce the TSR, as the vibration and noise generation is a cause of concern. To reduce the TSR, we would suggest increasing the chord length of our design, which would, in turn, increase the solidity of our turbine and reduce the TSR. Furthermore, our design proved to be stronger than it was needed to be. Therefore, the thickness of the blade at the root could be redesigned to be thinner, thus reducing the weight of the turbine and increasing our merit function.